In the last video, we know 3 interesting methods to calculate square roots. We are going to explain why these methods work. Firstly, we have long division. We use square root of 42 as an example. In the first step, we write down the number whose square is just less than 42, in this case 6, and perform subtraction like you do in division. Since square root of 4200 is equal to 10 times square root of 42, we can move the decimal point one slice to the right without affecting the quotient. Then we want to have 60x squared just under 4200. And from the subtraction process, we have 4200 minus 60 squared equals 600. Doing expansion on the first expression, we have x times 120x just under 4200 minus 60 squared. And the second expression tells us that it is 600. So we have x times 120x just under 600. This is exactly why in the next step, we will multiply 6 by 2 to get 12 and look for the number x, so that 120x times x is just under 600. This explanation can be generalized to every slice and every square root. Secondly, we have continued fraction. There are 2 bits we want to explain. First, why does truncating at a finite layer gives approximates? And second, why does the multiplying and adding thing work? In case you forget the multiplying and adding, this illustrates the process as taken from the previous video. For the first bit, we use square root of 5 as an example, which has the continued fraction expression shown on screen. We denote everything in the ellipsis by x, then x has to be between 0 and 1. By letting x equal 0, we have the fraction to be roughly 2.236. And by letting x equals 1, we have the fraction to also be roughly 2.236. Since x is between 0 and 1, the real value of square root of 5 must be between these 2 fractions. As you can see, these 2 fractions are already very close to each other, and in fact closer when we truncate it at a lower layer. Therefore, the sequence of truncated continued fraction would get closer and closer to square root of 5. For the second bit, the main thing we need to prove is this white boxed formula, and we would use mathematical induction to prove it. If we want to prove a statement is true for all natural number n, we first have to prove that when n reaches the smallest possible value, the statement is true, also known as the base case. And whenever the statement is true for n equals k, it is also true for n equals k plus 1, also known as the inductive step. Then the statement will be true for all natural number n. So for the base case, it is n equals 2, because the statement does not make sense if n is anything lower than 2. So we replace the statement by the case when n equals 2. But before that, we need to make sense of what P0, Q0, P1, and Q1 are, so we proceed as shown. Put these aside, we now focus on P2 over Q2 and write it in full. Now we want to have a little algebra. Now notice from the left, we have P0 equals A0, so we replace A0 by P0 here. Then do the same for Q0, P1, and Q1 respectively. This is exactly what we want to prove, so we have successfully finished the base case. For the inductive step, remember that we want to prove the case for n equals k plus 1 based on the assumption that it is true when n equals k. Now, like what we did for the base case, write down the definition of pk plus 1 over qk plus 1, which can be written like this. Rewrite the continued fraction in the denominator as shown. This is for less ambiguity when we move on. We can write this fraction to be a new pk over qk. Now since this is true for all k, we can decrease the subscripts by 1 and 2 to get these two relations. Now based on this yellow box, which is assumed to be true, we can rewrite the fraction here. Remember that bk is actually ak plus 1, so we can do a simple replacement here. By doing some algebra, we have this. Look at the white boxes. We can again do some replacements in the denominator. Similarly, for another set of white boxes, we can do replacements in the numerator, which is exactly what we want to prove in the first place. With both base case and inductive step done, we can prove that the formula is true for all n at least 2. I know that it is a lot to take in, especially the inductive step, so pat yourself on the back if you can follow so far. Rewatch the entire proof if you want. The third method is Babylonian method. The basic idea is to improve the original guess by taking the average of the previous value and a over the previous value. But why does it work? Let's say the distance between a0 and square root of a is less than some error bound epsilon. Square the inequality, then divide it by 2a0, and we claim that the boxed expression is a better estimate than a0, so we write it as a1. Now look at these two error bounds. a1 is a better approximate if epsilon squared over 2a0 is smaller than epsilon, which can be rewritten as epsilon smaller than 2a0. But what does that mean? Substitute this back to the original error bound, and with some algebraic manipulation we have this inequality. Since square root of a is positive, it must be greater than 0. Rearranging, we have a0 to be larger than 1/3 of its actual value. That means whenever a0 is greater than square root of a divided by 3, the error between the iterations and square root of a would get smaller. But what about when it is smaller than square root of a divided by 3 but still positive? Remember what we have done. This boxed expression tells us that a0 squared plus a divided by 2a0 is actually larger than square root of a. So a1 is then larger than square root of a, which is of course larger than square root of a divided by 3. So what does that mean? Whenever a0 is between 0 and square root of a divided by 3, then a1 would be greater than this threshold, and so the iterations thereafter would get closer and closer to square root of a. If you don't understand all these, there is a way to visualize what is happening. Here is the graph y equals x squared minus a, and the positive x-intercept is the square root we want to approximate. We select a very large a0, then construct the tangent to the curve at x equals a0, and the x-intercept of the tangent would be a1. And then we can construct another tangent at x equals a1, and the x-intercept of this tangent would be a2. So you can visually see that the iterations get closer and closer to square root of a. If a0 is much smaller than square root of a, then we similarly construct a tangent to the curve at x equals a0, and the x-intercept of the tangent would be a1. And we can carry on with what we have above. If you know calculus, here is a bit of detail why the iterations from the visual process are the same as the one that we have been talking about. From the definition of derivative at the point being slope of tangent, we have this general formula. Some of you might recognize this as the Newton's method. Since f of a0 and f prime of a0 can be readily calculated, we substitute it back to the Newton's method formula. With a bit of algebra, we can see that it is exactly the same iteration we have seen before. The next video is about whether each of these three methods can be generalized to cube roots. Subscribe if you want more of these math videos. See you next time!